Okay, so hello everyone. My name is Kunal, and I'm your physics tutor. And we are actually doing oscillations. And today is our lecture number 10. So let me quickly recap the things कि हमने previous class में क्या क्या चीजें cover करी थी. So in previous class we are actually learn about the simple pendulum with a case like in a simple pendulum under the influence of other forces, right? This is basically our main target जो था. The main thing we have to find is the time period of the simple pendulum. इसमें हमने तीन चार cases discuss करी थी. The first case is like our simple pendulum is kept in a accelerating car and उस पे हमने proper force method लगा के हमने time period calculate करा था. So वहाँ पे आया था 2 pi root under L by A square plus G square, where A square is the acceleration of the car, right? The things that we derive after this is actually a shortcut जहाँ पे हमने simple pendulum under the influence of any other forces, we can directly write its time period with the help of like 2 pi root under L by. We have to just write the G effective, right? And we also derive the formula of the G effective, which is actually is equal to root under G square plus A square, where A is the accelerations due to the other forces, and plus 2A G cos theta, where theta is the angle between the G and the A. That means acceleration due to gravity. And let us suppose this is the angle theta between A and the Z, right? So theta is the angle between the A and the G. And we have to directly write the as basically as we calculated the G effective, so we can find the time period easily, like with the formula 2 pi root under L by G. The next thing we are actually discussing this is some problems like there is a car which is actually on the bridge, you can say, or on inclined plane, and in which a simple pendulum is kept. So what is its time period, right? So इसकी time period हमने निकाला था, which is actually I think 2 pi root under L by G of cos theta, which is where theta is actually the angle of inclinations, right? That means it does not depend upon the amplitude, it just depend upon the inclination angle. So these are the things that we derive in our previous class. So in today's class, we are going to discuss about our new system, which is termed as, let me write it here, which is actually termed as compound pendulum. In other sense, we can also call it as a physical pendulum. So, okay. So what it is? So let me write its definition. So basically, it's a rigid body of any shape, which is actually free to oscillate about its suspension point, is called a compound pendulum. Like in simple pendulum, what we have a string and we have a small mass, which is actually oscillating about its suspension point, right? If I take it to the extreme position and leave it, so it start oscillating. So in compound pendulum, we have actually any rigid body, जिसकी shape कुछ भी हो सकती है, and which is actually free to oscillate about its suspension point. So let me write it here. Its definitions. So rigid body of any shape, actually which is free to move, about free to move, or you can say oscillate about the suspension point, is called like compound pendulum, right? So this is the thing, this is actually definition, like the any rigid body which have actually which is actually free to oscillate about the suspension point. So the system is called as compound pendulum, and of any shape, like the rigid body of any shape. So let me try to draw a figure here. Let's choose the white color. Okay, so I'm assuming this is actually our suspension point, and okay, and this is actually our system, some rigid body. It's like pot, you can say, right? And there is its actually uh suspension point as it's kind of pot, and similarly, right? And this is actually the theta angle from vertical, right? That means I'm taking it to the, let me make it in a clear way so that you can understand. Let me take some other figure, which is actually of rectangular face. So that will be easy to, okay. So let's take here a suspension point, and this is actually a rigid body. What I'm trying to say, I'm just, okay. So this is actually a suspension point, and what I'm doing, I'm just rotating it with the angle of theta and left theta. So that means this is actually its extreme position, right? So what I'm trying to say is, let me first write what are the points. So S is actually suspension point where it is there. Let me make in a better way. I think it's not visible. I have to use how can I draw this? I can draw it by using line actually, or I can use this. Yeah, that's fine. So what I'm trying to say, let us assume this is actually our suspension point, and this is actually our I'm drawing for the previous figure. So let us assume that this is actually our suspension point S, and this figure is actually rotated by some angle which is actually theta, right? Like this is actually our original figure or original body, and this is actually our rotated body, right? And I am rotated the figure with the angle of theta. So what I'm trying to say now is, and actually I'm rotating it about suspension point. So, and let us assume the body has some center of mass, which is actually there, somewhere there, CG, right? So CG is actually, you can call it as center of gravity. And basically L is the, and let us define a term L, which is actually the length of separation between suspension point and center of gravity, right? So basically there's a this distance is actually L, where L is the distance between the suspension point and the center of the gravity. So this is actually its mean position. This is actually displaced position, or you can say extreme position. Now we have to write the torque at displaced position. So at extreme position, or you can say at displaced position, the restoring torque is actually is equal to, look at it, the mg force is acting vertically downward, and this component is actually, we have to take the perpendicular one, because this torque will be counted as 0, so this angle is theta. So our torque is nothing but mg L sine theta, right? Now what we have to use? We have to use an approximation here, and the approximation is same. We have to consider for theta less than 4 degree, or you can say theta is tending to 0 degree. So when we use this approximation, what we get actually sine theta is equal to theta. And now our restoring torque is actually is equal to minus mgl theta, right? Now look at here, minus mgl theta. Now what I'm trying to say is, uh, this is actually our angular simple harmonic motion. Why? Because the restoring torque is the linear function of angular displacement, right? So this is actually our omega square term. So we have actually torque is equal to I into alpha and minus mgl into theta, and we have actually we don't know, because the rigid body can be anything, right? In this case, we are uh, basically assuming some kind of square plate. In different cases, it will be different, right? So I'm just taking it as I about suspension point. So alpha is equal to minus mgl by moment of inertia about suspension point into theta, where is is moment of inertia about suspension point. So this is actually our omega square term. And now we get the relation between the angular acceleration and the angular displacement. And this is actually our omega square term. So we can directly write the time period is nothing but 2 pi root under 2 pi by omega. So it will be like mg. So this is actually our time period for the compound value. I hope it will be clear to all of you. Let me tell you again, so it will be easy to understand to you, right? So what I'm trying to say here is, first try to understand like in simple pendulum हम लोग क्या कर रहे होते थे, हमारे पास एक स्ट्रिंग हो रही होती थी एंड उस स्ट्रिंग पे नीचे एक स्मॉल मास अटैच्ड हुआ था एंड वी आर टेकिंग दैट मास टू द एक्सट्रीम पोजीशन एंड देन वी लेफ्ट इट सो इट स्टार्ट ऑसिलेटिंग, जिसके हमने टाइम पीरियड निकाली थी, तो इट विल बी इक्वल टू 2 पाई रूट अंडर एल बाई जी. नाउ is this the only system which oscillate? We can oscillate anything. Like if you take a square plate, अगर आप एक square plate अपने हाथ में लेते हो and take it to the extreme position and then lift it, right? So it start oscillating. So the same thing is actually compound pendulum. So in compound pendulum, the mass attached is any rigid body of any shapes which is actually free to oscillate about its suspension point, right? So this kind of system is actually called as compound pendulum. That means किसी तरीके की system हो सकती है, मतलब कोई भी rigid body हो सकता है, किसी भी shape की हो सकता है, and उसको आप basically एक ऐसा काम कर सकते हो. Let me give you an example. Just try at your home. एक क्या आप कर सकते हो कि just take a nail and उसको wall में ऐसे लगा के and take a plain paper and उसको ऐसा इसमें ऐसा फंसा देने के, and then take it to the some angle and left it start oscillating, right? What I'm trying to say, take a piece of paper, एक plain paper ले लो आप और एक nail ले लो, ठीक है? and उस nail को क्या करो आप कि wall में लगा दो and then do a hole in the piece of paper and just attach it to the nail, right? And then take the paper to the extreme position and then lift it. It start oscillating. Not for a very much time, but it start oscillating for just few of seconds. So the same thing we are discussed in here. We can consider about the any rigid body and of any shape which have actually suspension point and which is actually free to oscillate. We are actually जब इसमें problem discuss कर रहे होंगे तो आपको अच्छे से चीजें समझ में आएंगी. So don't worry about the system kind of thing. जितने problems देखेंगे उसमें नए नए तरह के system रहेंगे. So you can apply those things also on your own, right? So what is our motive here? So our motive here is to calculate the time period of the compound pendulum, right? So what I'm considering here, I am considering here a piece of paper, you can say, or square plate, anything, and I am actually rotate it to the and basically, and I am actually doing the angular displacement theta with respect to the mean positions, right? Then after that, I am using actually the force method to calculate the time period. So actually what the thing we needed, the things we needed is at the displaced position, we needed the restoring torque. And then we have to create a relations between angular acceleration and the angular displacement. And you can also use the equations of the mean position, right? But here actually at mean position, there is no restoring torque. So we get no equation at the mean position. So we directly move to the displaced position. On displaced position, we have actually, there is a whole rigid body. So we have, and the in rigid body mass is continuously distributed, right? So where we have to consider the mass. So I hope you all learn about the center of gravity things. That means it is actually a point where you can assume the whole mass of this rigid body, right? Basically, in center of mass chapter and momentum conservation, you already learned about the term center of gravity. So let me recall you. The center of the gravity is the point where you can assume the whole mass of the rigid body. So the same thing I'm doing, I am actually assuming the whole mass of the square plate at the this point, which is actually our center of gravity. And I am actually uh, considering uh, and actually I am defining the length L, which is actually the distance between the suspension point and the center of gravity, where actually we are assuming the whole mass of the rigid body, right? And now I'm writing, now our system is actually, now our this system is actually turned into a system of like a simple pendulum, where the whole mass is, this is actually our center of gravity, where whole mass of the rigid body is there. And this is actually the length, suspension point, and the center of gravity. So we are actually converting this compound pendulum system to a basically simple pendulum, right? I hope it will be clear to all of you. Let me tell you again. मैंने यहाँ पे क्या किया? I am considering the whole mass of the rigid body at its center of gravity, because center of gravity is the point where you can uh, assume the whole mass of the system or the whole mass of the rigid body, right? So I am writing the whole mass of the this square plate as m. Let me call it as m, and the point is actually center of gravity. And we have a, and I am defining a length L, which is actually a distance between the suspension point and the center of gravity, where we can assume the whole mass of the system or the whole mass of the rigid body, right? So now this system is actually turned into a uh, simple pendulum. So which have mass actually 2 pi root under L by G, right? Or we have to write the equations. So the same thing I'm doing here. I'm just writing the equations at the displaced position or the extreme position. So we get the time period formula is actually nothing but T is equal to 2 pi root under I about suspension point. Why I'm assuming why I'm not writing the MLS square? So the reason is actually we have, I am actually writing in the definitions of the compound pendulum, actually the rigid body of any shapes, not a concrete, it may be of like something this kind of shape as well. So we have to this system has not ML square as a moment of inertia. So we have, so I'm just writing it as I about the suspension point. It's actually different for the different kind of system. So when we deal with the problem, it will be clear to all of you, right? जब हम लोग प्रॉब्लम देख रहे होंगे तो ये सारी चीजें क्लियर हो रही होंगी. The things that you have, and I derive the formula, the things that you have to remember here is the time period for the compound pendulum is actually 2 pi root under moment of inertia about suspension point divided by mgl, where L is the actually distance between center of gravity and suspension point. So this thing you have to remember. Okay. So let's move to some kind of problem here. So that it will be clear to all of you. So what I'm doing, let's take a ring. Okay. Question 1. I'm assuming there is a, or take a bangle, right? Take a bangle, or let me draw it here with the help of that. So that will be more clear to all of you. Let's take the red color. Okay. So I'm taking a bangle here, and I am taking here as a suspension point. That means यहाँ पे इस बैंगल को नेल करके ऐसा क्या उसको बोलते हैं, हैंग कर दी गई है, राइट? द actually the bangle is hanging at the nail. So this is actually its suspension point. And what is actually given? So actually given is bangle is a kind of ring, right? Is a kind of ring who has mass m and the radius r is given, right? So you have to find the time period of the bangle, right? So अभी तक जो हमने करा था उसमें तो हमने क्या क्या चीजें देख रहे थे, हमने देखा था कि सिंपल पेंडुलम होता था जिसकी टाइम पीरियड हम निकाल रहे थे. बट देयर इज अ सिस्टम लाइक बैंगल्स काइंड ऑफ थिंग. हाउ कैन वी कैलकुलेट दिस थिंग? So this is actually our compound pendulum, right? And we all know that the formula for the time period for the compound pendulum is 2 pi root under I about suspension point divided by mgl. We actually derive it here, right? Now we all know that. Let's try to find the first is. And where is this? First try to find the system कि इस सिस्टम का सेंटर ऑफ ग्रेविटी कहाँ है. So we all know that the center of the gravity for the ring or the disc is at its center. So this is actually at center of the bangle. The center of the gravity lies, right? So first we get the things like center of gravity. And so we get the things, one more thing we get, which is actually the length. And the length is actually defined as the distance between the center of the gravity and the suspension point. And the distance is actually nothing but our radius r, right? Because our center of gravity for the bangle is at the center of the bangle. So the distance between the suspension point and the center of the bangle is actually radius of the bangle. Now we have to calculate the moment of inertia about the suspension point. So we all know that the moment of inertia about the center is actually mr square. And then we are actually applying the parallel one. So like mr square plus mr square, right? So it will be actually equal to 2 mr square. How it will be? Because at center of mass, it will be actually equal to mr square, and we all know that from parallel axis theorem. I hope it will be clear to all of you. आपने moment of inertia वाले chapter में पढ़ा होगा parallel axis theorem, which is actually saying I about S, let us call S. So I about center of mass plus m into d square, where d is actually distance between, and both should be parallel, right? And d is the distance between center of mass and S, right? So the same thing I'm doing here. Okay. अगर आपको क्लियर नहीं हो रही है तो आप इससे कनेक्ट कर सकते हो. दिस इज एक्चुअली आई एम यूजिंग द पैरेलल एक्सिस थ्योरम because the moment of inertia about the center of gravity is actually mr square, and then from parallel axis theorem we have to find the moment of inertia about the suspension point. So and the both is actually parallel. So we use the parallel axis theorem. So about center of mass is mr square and plus md square. So d is here is the distance between the center of gravity and the suspension point, which is actually r. So 2 mr square, right? Now let's try and now let's write the time period. So time period is actually equal to 2 pi root under is actually equal to 2 mr square and divided by mg, and L is equal to actually R. So get cancel, R get cancel. So it will be actually equal to 2 pi root under 2R by G. So this is actually the time period of the bangle, right? So हमने यहाँ पे क्या सीखा कि अब हमारे पास किसी तरह की भी सिस्टम दी हुई हो, we are able to actually calculate its time period, because चाहे कोई भी रिजिड बॉडी हो, किसी भी शेप का रिजिड बॉडी हो, we can easily calculate its time period with the help of the formula of the time period of compound pendulum, right? Now let's take the another system. Okay, so I hope this problem is clear to all of you. Let me tell you again if it is not clear. I'm just taking the your first goal is to find the center of gravity of the rigid body. So it for bangles, it will be at center. And the second thing that you have to find is the distance between the suspension point and that of the center of gravity. So we get, which is actually equal to the radius of the bangle. The third thing you have to find is the moment of inertia about the suspension point. So we actually know the moment of inertia about the center of gravity or about the center, which is actually mr square for the in case of ring or bangle. Now the next thing you have to do is you have to find the moment of inertia about the suspension point. So we are actually using the parallel axis theorem because both are parallel to each other. So we are using that. So in parallel axis theorem, what it is actually I about suspension point is actually equal to I about moment of inertia about the center of gravity or center of mass and plus of md square. So where d is the distance between the center of gravity or center of mass and suspension point. So in this case, our d is actually is equal to r. So it will be like mr square plus mr square, which is actually 2mr square. And we just put those value of L and IS in the formula. So that you have to basically find the two things only, right? First thing is uh, L and second thing is I about suspension point. So I hope now it will be clear to all of you. Now let's take the another problem based on this. Now what I'm considering here is actually I am taking a rod here. Let me draw it here because से clear नहीं बन पाती है. Let insert straight line here. Let insert another straight line here and another straight line. Another straight line. Okay. Now, so this is actually our rod, and let us assume there is its actually suspension point. Right. I'm assuming that this rod is actually hanging at nail. Right. And the things is actually given. A rod has a mass of m, and the length of the rod is actually L naught. Right. So what I'm assuming here. So what I'm assuming here, the rod has a mass m and the length L naught. I'm not assuming, actually it is given. Sorry. And you have to find the time period of the rod. Right. So this is again, actually it's a rigid body. And so this is actually the example for the compound pendulum. So we have to find its time period. So what we have to use? We have to use like time period is equal to 2 pi root under I about suspension point. So this is actually its suspension point and divided by mg into L. So we have to find the two things. So first thing we have to find the center of gravity. So for the rod, the center of gravity at its midpoint, which is actually from suspension point, its distance is actually L by 2, right? So we get the L, let me call it as L dash here because, okay, no problem, no problem. So L is equal to actually L naught by 2, right? Because the length of the rod is actually L naught. So the distance between the center of gravity and the suspension point is actually L naught by 2. The next thing you have to find is I about suspension point. So actually there is a direct formula for the moment of inertia about its end point. So what I'm using for rod, we have a direct formula. We have a direct formula for moment of inertia about its end point. And what it is actually m L naught square by 3, right? So we have directly put it here. So the time period is actually nothing but 2 pi root under m L naught square by 3 and mg and L values is like L naught by 2. So this and this get cancelled. So we'll simply get 2 pi root under 2 L naught by 3g, right? So this is actually our time period formula. I hope it will be clear to all of you. right? The next thing we have to find, let's take the another example with a solid sphere, and we can also look it into uh, semicircular ring and all. So we are actually our main goal is to look into the most kind of system uh, via which you can assume that it is a best example of the compound pendulum, right? So the things that you have to do is simple. You have to find the its center of gravity of the rigid body, and then you have to find the distance between the suspension point and the center of gravity of the rigid body, and then you have to find the simply moment of inertia about the suspension point. And if you find these three things, if you are able to find these three things, you just have to put the uh, value in the formula, right? Now let's take the another example, which is actually the solid sphere. We have actually a solid sphere is given, which has a mass m and a radius r. So let's draw. Let's take some other color. Let's take this time some green color. And let's take it here. Okay. Let's take it as a small. That's fine. And we have to draw a straight line. Okay, that's fine actually. I hope it's not extended to some. Okay, that's fine. And actually it is a solid sphere. So I hope it will be clear to all of you. This is actually an solid sphere. So I'm just doing, okay. And let us assume there is its actually center O. And okay, so you have to, and its suspension point is there. So you have to find the time period. So my suggestion is to pause the video and try to find it by one because it's easy now. So time period for solid sphere. So we all know that this is actually a rigid body. And so it is actually the example of the compound pendulum. So our time period is nothing but 2 pi root under I about suspension point by mgl, right? Where actually L is the distance between the suspension point and the center of gravity. So the first thing we have to find is the center of gravity. So which is actually lies at the center of the, and this thing actually given, you can, the distance between the suspension point and the center of and the center of the solid sphere is actually given, which is actually equal to L. So here we actually, first thing we get, this is actually its center of gravity. And the second thing is get like L is equal to L naught. This is actually given. Now you have to find the I about the suspension point. So we have to use the parallel axis theorem. Why? Because we have the formula for the moment of inertia about this, actually about the center of the solid sphere, but we didn't have formula for the other point. But it, that means direct for the other point. So we have to use the parallel axis theorem. So it will be actually is equal to I about center of mass plus md square, where actually we know that d is the distance between d is the distance between center of mass and suspension point. So in this case, actually D is actually our L naught. So we can take it under consideration. Now, what is the formula for the moment of inertia about its center? So it is actually in case of solid sphere, it will be like 2 by 5 mr square and then m. And for here, D is actually L naught. So it will be like L naught square. So we have, this is the for I about suspension point. Now we have to find the time period. So time period is nothing but 2 pi root under 2 by 5 mr square plus m L naught square and divided by, we have actually mgl, where mg and L is actually nothing but L naught. So we can write it into this form. Time period is, let's take m common, 2 by 5 r square plus L naught square divided by mg L naught. This and this get cancelled. You can write 2r square plus 5 L naught square divided by 5g L naught. So this is actually our time period. I hope it 2 pi is missing. So yeah, this is actually our time period. 2 pi root under 2r square plus 5 L naught square by 5g L naught. I hope it will be clear to all of you कि अब आप किसी भी तरह के सिस्टम दे आपको दी हुई हो, आप उसके टाइम पीरियड को इजीली कैलकुलेट कर सकते हो, राइट? I hope this thing will be clear to all of you. Let's take the last example, which is actually on semicircular ring. Let's take the semicircular ring. How to insert it? Let me try it here. This is actually our full circle. Am I able to delete some part? Oh no. Okay, left. I think there's no direct figure to draw it. Let's take it here. So question number third. So we have actually one thing is given, which is actually a semicircular ring. You can assume in this way, right? There is actually nothing. So, okay. And we have a suspension point is there only. And its radius is actually R. Okay. So this is actually a semi-circular ring. And the things is given, it has a mass M and the radius is R actually. Okay. Yeah, it is actually given the mass is M and the radius is R. And you have to find its time period where its suspension point is this. So my again suggestion is to pause the video and try to solve it by your own because it's now easy. So you have to find the time period about suspension point, not about suspension point. Just try. It's actually wrong statement. Okay. So you have to find the time period. Time period is equal to what? Okay. So what we can do it here? We can do the first thing we have to find its center of gravity. So the center of gravity for the semicircular ring is actually from its center. It is actually lying 2r by pi distance upward from the its center, right? So there is the center of gravity of the semicircular ring, right? So you have to find the L. So L is actually r minus 2r minus pi. So we can say 1 minus 2 by pi into r. This is actually our L, right? This is actually our L. Because L is the distance between the center of the gravity and the suspension point. And in this case, the distance between the suspension point and the center of gravity is actually the whole distance r and minus the center of gravity, which is actually 2r by pi distance upward from the center. So this is actually our L. Now the next thing we have to find is the I about the suspension point. So it is actually same, but we have to consider it here, right? So from parallel axis theorem, the I about the center of mass, right? And plus the distance between, plus the distance between the center of mass and the suspension point, right? So plus m into d square. So you can also call it as, let me write it here. So actually mr square plus m into 4r, because 2r by pi is the distance between the center and the center of gravity. So it will be 4r square pi square, right? Actually the whole, actually here the minus because we are considering it from there, right? So you can either call it as r square minus 2r by pi square, or you can call it as in this way. So here we have mr square. We can solve then pi square minus 4 by pi square. So this is actually our I about suspension point. So now here we get the time period, which is actually equal to 2 pi root under I about suspension point. divided by mgl. So our L is actually 1 minus 2 by pi. So when you write it here, you get the things like 2 pi root under 2r square pi divided by gr into pi minus 2. Okay, try to simplify it, you will get the same value, right? The things that you have to keep in mind is, okay, wait, I think I did a small mistake here because pi by 2 and pi by 2, the term will be get cancelled, right? You have to first find the I about the center of mass. So it is actually plus, and when you solve this, actually you will get, let me write it here in a clear way, because you have to find first the I about the suspension point, I about the center of mass, then you have to find in the next way. Okay, wait. First, you have to find the I about center of mass, because we only know that the I about the O. So you have to find here the I about center of mass, which is actually I about O plus m into the distance between the O and the basically DOC square, right? And this is actually DCS square. So when you solve this, you will get the final value about the moment of inertia about the center of about the suspension point is, because we have to find the moment of inertia about the suspension point, which is actually you finally get as 2mr square by pi into pi minus 2, right? And when you apply it here, what you will get? You will get simply 2 pi, because pi minus 2 get cancelled, so you will simply get 2r by g, which is actually same as, if you look at here, it is actually same as what you calculated for the complete ring, right? So the time, either you can take the half ring or you can take the full ring. The time period for the both of the ring will be same, and it is actually equal to 2 pi root under 2r by g second. Look at here. For full ring, we actually get the answer. The time period is actually 2 pi root under 2r by z. And for the semicircular ring, it is actually also same, and which is actually equal to 2 pi root under 2r by z. I hope it will be clear to all of you. So that's all for today's. In next class, we are going to discuss about the things like small angle approximation. So thank you.